then we have the axis, then we have somewhere here we have the bearing, if I'm not mistaken, another type of thing like this. And get you a steady state part of the state of the machine, or you can do a transient. And that's actually one of the interesting parts of MotorCAD, is that it can do duty cycle. Duty cycles are very important. We'll talk about it a little later. Okay, well, that was quick. So if I try to start it from my notes, I want to start this way. And let's see, make sure that all of this works fine, all programs, MotorCAD. That's good. It seems that I still have a valid license. I'm a lucky fellow. So here is the input. If I look at the input, first we have different type of machines. So if I look at it, motor type, we have the brushless, regular brushless machine, induction machine, and you can see as I go along it's going to change the type of things. By the way, what you find is almost the same thing as you find in the overlays. Okay? All the overlay we talked about this morning with Flux, you find the same geometry here. And a little more. Sorry, geometry. Motor type, we have outer rotor, okay, all of those things. So this is just a regular brushless machine, but the rotor is the one that is turning. And I'm going to go a little further. We have, okay, the brush machine, so now we're going to have brushes also associated to this. And then maybe another type of motors, the clopole machine. So this is essentially a 3D type of machine. Actually, if I look at the 3D pictures, that's not as well, but you can see the claws that come from the other side. Just think about the claw type of a structure. And this is a permanent magnet, actually, we're seeing. Let's see, other type of motor type, the Whitefield machine. No, this is not the, what did I send it to you? Interesting. That's not what I was looking for, but in any case. Anyway, so single phase machine, you can actually have the distribution of the slot also. So let's stay on the brushless machine. We've talked about it. Well, we don't care. Okay. This is a brushless machine directly. And now we can see here, I have all the information. We have the two threads, we have the slot opening and all of the things. And as I change information on the go, let's say I'm going up to 9 millimeters in opening, and you can see that the teeth actually were just changed very quickly. Also, I have a little green marker that shows me what I have changed. So this is very cool stuff. I can actually track my changes as I go along. The other things we can do, you can see here you have the cooling. So setting the geometry of the machine is not enough. We need to set all the information necessary for the cooling. So we can have no cooling at all. Here we go. So it would be just the frame as it is. Or we can have any type of fancy or not so fancy type of coolings. In this case, those are radial fins, so I will see them only in this direction. Okay? So I'm going to put something that doesn't have any cooling here, take round. It could also be mounted or not mounted. We'll look at it otherwise. The magnet could be on the outside, but they could also be embedded. Okay, we'll just keep the regular type of magnet on the top surface radial. And then you could have also cooling duct and stuff like this. So here we don't have any, but I could actually add some duct inside the rotor at this point, and we'll look at how it's actually going to behave after. So I'm just not going to put any at the beginning, but you can think about a lot of stuff. Also, I didn't say it, but in the housing we could have water channels and stuff like this. Then once we have the radial pictures, we can go to an actual picture. So here we have the whole machine. We see here, for example, we have a lot of end space in the front and in the back. So I could change, for example, the length of the motor. I'm okay. Let's see. I wanted to get the extension. I'm always having a little time to do those things. Just change something so I can show you that. Let's bearing rotor plates. Okay, first one is the winding extension here, so that's the extension. So you always want one for the front and one for the back. So I can put the winding up to 8, for example, and do redraw. Well, I guess it doesn't want to redraw in my case. Normally it should actually see me as I go, show me as I go along how the geometry is being oh, that's what's the extension. Yeah, you see here, this extension is longer in the front than in the back. So of course, after I have the end winding overhang, so in this case it's 30. Okay, thank you. Let's go back to here. So in front, I'm going to put them at 40, for example. And now the end winding in the front are actually. So I can adjust to whatever my machine is supposed to be. Okay. We can mount it. Right now it's on the flange. I'm going to remove the flange. It could be mounted on the foot or both of them together. And then this is a little cool stuff. It actually shows you the pictures. You can see the end windings are being removed from the front. Here I can put them back in. Now I can see the machine. I can turn on and off different type of things. So that being said, now that I have my geometry, then I can look at my winding. That picture is actually a representation on the ratio of copper to insulation. So the copper is in yellow and the green is the insulation. It's not one this way, but it's the way it is. So the first thing is we could have non-overlapping winding, and in fact we can even have them with just an air divider in the middle, no solid dividers. Then the winding is defined by slot fill. Here I have a slot fill of 0.6113, which is already pretty good. But say, for example, I can put 0.7, and what you can see is that the ratio of yellow to green has actually changed. Okay, different things in the area. This is defined with a wire gauge also, so that's how we actually decide of all of this. So winding, could be impregnation, no impregnation, so we'll just put air for now. It could be potted or not potted, so you will see it on the end winding, and then the wedge could be conductor or non-conductor. That's the wedge right here. Input data, so that's the other important part. So the first thing is the losses, of course. And so the losses, you would actually get them from a tool like Flux, or speed, or any type of device, or you could have it for measurement you've done also. So you are going to enter all the data for one specific speed. Now remember what I told you? I told you that we can have duty cycle, so we need to have the law that will define how the losses are going to vary with the speed. So in this case, we have the reference speed is actually 3000 RPM. Well, we'll talk about the variation after. 120, this is losses in the copper, we have losses in the back iron, losses in the stator teeth, stuff like this. We have the bearings, so I can say I'm not really interested in the bearing, but let's put also some losses in the magnet. Say, for example, I have 5 watts in the magnet, which is not too bad. Rotor back iron, there should not be anything because it's a brushless machine, so there is very little. Losses of the windage, we have 10, and this is losses if you have a fan also associated to it. So those are all the reference value. We see the variation of the power versus the speed, and you can see it's in the ratio of the reference speed to the speed you are working at, and it's with the coefficient. So now we can actually have a little coefficient to say how much the speed is going to affect us. So of course, if we talk about windage, this is where we have the most influence with the speed, okay? For the core losses, well, we can say we are at constant current, and so the core losses are going to stay the same, and things like this. So we could also have the losses depending with the temperature. This is to adjust to the fact that copper changes with temperature, the resistivity. Okay, and then we could also distribute the losses inside the different slots. So once we have the losses, we need to talk about pooling. And that's the different type of cooling you want to have. So if we put any liquids, we're actually going to have to select the liquid here. For now, we'll just keep the natural convection, ambient temperature, stuff like this. We'll just keep all of this. Then you have the materials, so you can select one by one the materials. So for example, if I get to the stator lamination, I can actually select the type of lamination I have. So iron steel, stainless steel, well of course it would be iron steel with grain oriented, or a percentage of silicone, so 2% silicone steel for example. And then it will adjust all the coefficients. So there is a material database which is quite extensive, but there are also information that are by default here, so I'm just going to keep those. And then there are a lot of different things here, like you can set air gap, interface air gap. So if you don't have very well tooled pieces, you know, you may have a ragged surface, and it will give you a little interface. And then all the things. So natural convection. I said I would have natural convection. So now I can say where I want natural convection. So I have on the housing, and I have on the end cap. Why not? I don't know why I would not have it. So I put natural convection everywhere. And then information about the end space, if there is some wind edge going on, stuff like this in it. And then there is information about duty cycle. So we can install all type of duty cycle. So first, I can just do regular transient. Okay, so that means I'm going to start and let it go as long as I want. But I don't really care. I can actually define a transient. So the way I define the transient cycle, I'm saying from when to when it's going at a certain value of the torque, and then the speed as it goes along. Okay, and you can see that on top of it, I can play on the copper losses here. So I'm just going to keep all of this. I don't really going to do very much at this point. And there is more and more. So as soon as I have done all of those values, I can actually go here, and it's going to derive the whole topology and give me directly the temperature and all of those things. Okay. So in fact, we can see if I put higher losses. So say for example, I'm going to put 150 watts here. I can put a little more. Let's just say, well, actually this is already pretty good, but let's just put 50 here on the teeth. Now, as soon as I go here, the temperature are going to go up. I was at 120. I put a few more losses on the winding, so here it's coming here. So if I follow all of this, I'm going from, I'm actually going from the copper here, which is at 145, to the frame, 125, so it's pretty hot frame on the outside, okay? I really definitely want to cool this off, so I can see how I would do this. I can first work maybe on putting some fins. So we remember we were at 140. Actually, let's put the fin the other way. Actual fins, round like this. And let's look at the temperature here. So now from 140 I went down again to 120, and if I look on the outside I'm at 95, 98, so still a little high. We talked about putting other type of cooling. So for example, I can put here, and this is going to be very good. I put a water jacket. I can put it this way, or I can put it here. I'll put the water jacket this way, so you can see. Let me just not put the flow here. Here is the water jacket. So of course, if I put a water jacket, I'm going to have to go here and look for the cooling water jacket. And now I need to get a value. Okay, where is the water jacket here? I'm going to say what's cooling it off. So I'm going to do a ethanol glycol water mix here, and put this here. And if I look at it here, well, now I'm overcooling my motors. It's only 33 degrees. So basically I'm killing it off here. I don't want to do something like this. This machine would not require obviously a water jacket. There are some better things to do. So probably if we do some better things, or in fact let's do the film the other way around. Those one here. And let's look at it. Temperature. Here we have a 200 degree and kept 80 degrees. So I mean, we're within the kind of size that we want to do. So just quickly, the last thing. So first we have the circuit, and you can the cool stuff about it. This gives you the whole circuit. And now, if I want, I can actually add something. So for example, if I have, for example, something happening between the end ring and for example, the bearing, the front, and the end cap, I can actually create a node that would be there and put a resistance or something like this. So I can do quite a few things. The other interesting thing is I can do sensitivity study. We talked about it. And then the other thing is I can do the transient. So I'm going to let the transient go by here. And it's not going to be very long. Let me just go through at this point. Almost there. So what it's going to do, it's going to apply the duty cycle that I showed you before, which was very easy. Basically go constant speed, increase the torque, then goes down, etc. And I'm only applying once. So here we have a lot of information, but here we have some information about the winding. Here is information on the rotor side. This is actually, this is a stator teeth. The rotor side is probably at this level. So I can click any of those information. So here is a magnet. So the magnet is right there at the bottom. You get more than what you asked for at this time. So let's go back to my presentation here. So we're going to look at a machine here. It's a machine that runs at 3,000 RPM. The radial torque is 12 Newton meters. The peak torque is 36 Newton meters. It's fed off a 620 volt DC link. And that's the different information. 26 gauge and 19 for the lamination. I don't see the coil here, but anyway, all of this is right here. This is the size of the machine, and it's in an ambient temperature which is 40 degrees C, and it's going to be a totally enclosed machine. We want it in class F and with a housing water jacket. So, I mean, the important parts, I don't know if you know about the class of the machine, but basically what it tells you is that giving a winding temperature. So I said I was in the class F, so say if my machine works at 140 degrees, it's telling me that basically I can get 70,000 hours of machines. So that's something that qualifies a machine depending on the temperature, and this is why it's important to know the temperature we reach actually. Another reason why we need the temperature is because the characteristic of the magnet change with the temperature. For example, if I look at the remanent flux density of the ferrite, it actually decreases of 20% per 100 degrees. If I look on the neodymium, something we actually use a lot, it's 11% with 100 degrees. But not only does it change the remanent flux density, it also changes the coercitive field. So again, and not always in the same direction. So we have to be careful about all of this. So if we look here, for example, at a neodymium iron boron type of magnet, what we will see, those are the characteristics of the magnet for the ambient temperature, cold temperature, and hot. Now we have to be careful because if this was my open circuit load line, as I apply current, I'm going to move the line right and left, and you can see that if I go right here, I'm going to enter the demagnetization of the magnet, and very quickly I won't have the machine anymore. So we have the same for the ferrite and things like this. Other consideration, of course, the copper changes. So that means that if the copper increases in resistivity, given the same peak voltage, we'll have a current that is a little down. So that's not quite true, because if we have a high voltage bus, we should be able to get the same current no matter what. So, but in any case, we have some problem. If we were to actually lower the current, we would have less flux around the way, less torque. less effective machine, less reliable machine, and stuff like this. So here we see the description of the machine. I don't really care, I just showed you this. This is the information with it. So we're going to do first a steady state, then we're going to do a transient to see the time constant of the machine, and of course we could do the duty cycle. So if I do the steady state, what I found out is that the winding temperature is going up 142 degrees. It's going to 142 degrees, and if you remember, we started an ambient of 40. So the raise is 102 degrees. Here the raise is 93 degrees for the winding. And if I look at the housing, we're up to 125. Okay? And this is seen if the machine turns on and we let it go for 6 hours, so we'll see if we reach this. So the information before was just a steady state, so it assumed that it goes to infinity. So now let's say this machine is running for 6 hours straight, and this is the temperature I actually get, and you can see I'm at 140 for the coil, it was 145, so it's about the temperature I get. So it takes about 6 hours for the machine to reach the steady state temperatures. That gives you an idea of the time constant of the temperature of the machine. Let's see, this is on the rotor side. So the first one here was the stator. This is on the rotor side. And we can see on the rotor, we probably are not quite at the top. So it's still raising after 6 hours. And this is the housing. So the housing, what are we here? We are at 135 degrees. That sounds like it's a lot here. But that's probably the top where we are, okay? We did it. So, luckily those machines are not used 100% all the time, but they go through duty cycles. So here we are actually going to look at the duty cycle, where for 60 seconds we are going to go with the 3 per unit torque, and the speed is going to be constant. And then for the next 60 seconds we're going to remove the torque and just keep the same speed. And we'll do this 15 times. And now this actually shows you, so this is when we apply the torque, it raises, and this is when we let it go by itself, apply the torque and so. And so we can see for the 1800 seconds here, we can see that the temperature is still rising. Okay. So that's okay, all the different curves you have them in. So let's see how we're going to cool this machine. And in this case, let's try to work with water jackets. This is water jackets, it goes the other way. So 12 parallel channels, 80 degree, this is the temperature, inlet temperature of the water. Not the water, it's actually, we'll see, it's a mix actually. And then what we're going to do is push through 0.5 gallon per minute per channel. So each of those channel will see 0.5 gallon every minute, okay? And so that gives you, actually, if you look inside there, it gives you a velocity of about 1 meter per second. And then the fluid we're going to do is the ethylene glycol water mixture. It's 50%, I think. And so now, instead of the 140, no, it was 180, I think, before. Now we actually keeping the temperature well under check at 95 degrees for the winding, 55 degree raise. So that's actually quite acceptable. The magnet temperature is only 48 degree raise. And the housing, of course, where the water jacket is only 42 degree raise. So if we compare to before, 1, 2, so we basically divided by 2 the temperature. Here, almost by 2 also, and here also by 2. Okay? So that's just a little example to show you what kind of stuff we can do. I have quite a few examples, so let's talk about it. We have the sensitivity study, so I'm going to be able to identify the important parameters, same as what we did before with Got It. Duty cycle. So as I said, duty cycle can be very, very difficult. Here, I believe this is for aeronautics. So this is some kind of an actuator, so on an aeronautics, on an airplane type of equipment. And you can see how the torque actually is solicited at regular interval, and how the speed, however, is always the same. So if I talk about duty cycle, by the way, think about elevators. This is a very complicated duty cycle because you have every day of the week, Sundays, maybe an office building is closed, so the elevator is not being used. And then on Monday morning, everybody wakes up and go to work. So from, let's say, 6 to 8, it's actually very solicited. And everybody works and don't do anything. So from 8 to maybe 11, nothing happens. And so through the whole years. So you can imagine thousands of points on the duty cycle. And one of the things you can do is that you can import the duty cycle completely. So if we look at the result of this machine, it actually shows you through the duty cycle. We have the computation, it's all the little dots, so this is actually the winding. We measured the temperature computed on the side of the winding and in the center, and now we have a test, so now you have to be careful because it depends where you put your sensor for the temperature. But the cool stuff is we're right. I mean, the test doesn't really, we're on the safe side. It's always below the temperature that we evaluated, except maybe right here on the cooling, but you know, it's actually quite an interesting result here. Other type of things we can do here, miniaturization. So what's happening is that an old machine, existing machine, 50 meter of acting length, 130 long of housing, and now we're going to do a segmented motor. So what it means is that every tooth will be a set of lamination with a winding around, and then we take all the tooth and put them together. Okay? And so doing this, actually, we can be much more careful packing the windings, making sure there is connection, there is no air and stuff like this through. So now doing this, what we're going to be able to do, once we redesigned this machine, looking at the thermal part, we were able to reduce the active length, reduce the size of the whole machine, and still get 34% more torque for the same temperature. Furthermore, if we work on impregnation, and this is where it's actually interesting, because if you do those winding of the tooth, you can actually do very well, and so the impregnation can actually be done quite well. With even better materials, we can even get to 15% in reduction, which we translate in, so this is actually the potting and impregnation, that will also translate into a cooling machine, a cooler machine. Other type of things we can do, this is radial fin optimization, so look at the size and the spacing. Actually, I think this is just the spacing between the fin, trying to see what's the best temperature distribution. So you can see here, there is a space where you actually get something when if you put them too close, it doesn't work. And if you put them too far away, it starts heating again. That's an induction machine we did a long time ago. It shows you the whole machine here and the different ways. Eventually through just forced ventilation, and all the winding temperature is predicted within 5% of what is measured. This is actually the machine here with a full forced ventilation. If we put the forced ventilation, we actually put the characteristic of the fan. So we have the pressure and the speed, okay? And out of there we actually go get the losses. That gives you, this is a paper that was presented in 2002, it's very old, but it was very, very close in result. Type of duct, we have all this. So back analysis, this is a case where we have a machine which is being used in the water. We took it back and now it needs to lose its temperature. So the housing was actually in water initially. As soon as we get out of the water, there is the heat from the winding that needs to get out. The housing comes up, and it makes the machine very unsafe to handle. And I think, you know what? So I think this is about all what I wanted to share with you today. And I guess we have an open time for questions this time, or do you want to, how do you want to do? I'll give you the microphone back. You're the boss now.
今天很紧凑哈，有没有什么问题要请教？文生先。那我们谢谢两位精彩的。好，谢谢各位观众哈。燕州要不要？好。
好，非常谢谢今天大家来参与这个 Flux 的 User Meeting 的部分。那如果之后大家还有什么样的问题，可以再跟我这边联系。那如果对于今天的这个 PowerPoint 的部分，如果大家有需要打电子档的话，再过来跟我讲一下，那我再 email 给大家。好，谢谢大家。